Okay, thank you, sir. Are you hearing my voice, sir? Now I'll share my PPT. Okay, visible my slide, sir? Yeah. Now I put in full screen only. Sir, now okay? Sir, now okay? Okay, now verify, sir. Sir, now okay? Full screen open. Okay, now verify, sir. Sir, Prabhu, sir. And now full screen. Okay. Full screen open. Okay, now verify, sir. Sir, Prabhu, sir. And now full screen. Okay. Sir, now verify. Okay. Full screen open. Okay, now verify, sir. I shared full screen. Sir, Prabhu, sir. And now full screen. Okay. Sir, now verify. Okay. Full screen open. I given the full screen option only, sir. I shared full screen. Sir, Prabhu, sir.
Sir, no problem, sir. You can continue.
Now full screen. Okay. Okay. Sir, now verify. Good evening, 1.5% here. My topic, VLSI in semiconductor and AI analysis. I given the full screen option only, sir. I shared full screen field.
Sir, no problem, sir. You can continue.
Is now each and every movement. All are using good evening, VLSI technology here. That little bit introduction about in electronics. In Bodin Shockley on year 1947, Bodin Shockley and the Bell Labs, they are now each and every the first chip, the first germanium bipolar transistor. Roughly 50 years later, electronics account for 10%, that $4 trillion of the world GDP. And next, evolution of the electronic devices, the vacuum tubes, discrete transistor, SSI, MSI, integrated circuits, and nowadays using in VLSI, mount circuit, these things and all. And Moore's law, according to Moore's law, that date in x-axis for date of introduction and y-axis for transistor count. That microprocessor transistor counts 1971 to 2011. How that Moore's law playing that how that gates are nowadays used, and future size reduction enabled by process innovation. Sir, Prabhu sir, hearing sir? Okay. That's why I stopped. See, these are the basic. Allah knows that how they are 50 years before I developed these things and all. And after that, a little bit that welcome to and semiconductor materials and what are the materials in carbon, silicon, germanium, tin, gallium arsenide, gallium nitride, indium, and boron nitride, silicon carbide, and these are the semiconductor materials, but mainly used silicon and germanium only nowadays. Now coming to the point, introduction about that VLSI. That VLSI very large scale integration, many transistors on one single chip. So metal oxide semiconductor nowadays and the MOS transistor used in the design of the all electronic circuits. The metal oxide semiconductor MOS transistors are very fast operation, cheap rate, and low power transistor. Low power means it consumes very less power, very low power operations. And that a mixture of N type and P type leads to less power. That's why the called name is complementary metal oxide semiconductor. It's called CMOS VLSI design. Today, how to build your own single, that is a simple CMOS chip, TMOS transistor, building logic gates from transistors, and transistor layout and fabrication, and how to build the good CMOS, the things and all we are going to do here. And this structure is called silicon lattice. In the silicon lattice, transistors are built on a silicon substrate. Silicon is a group 4 element. Already that here that semiconductor material shown here, group 4 material. So in this group 4 material, the forms crystal lattice structure in the bond of 4 neighbors. According to this is the silicon lattice structure, and here given the dopants, silicon already told silicon is a semiconductor. This is a pure silicon, has no free carriers and conducts poorly. According dopants increases, the conductivity increases. Group 5, it means extra electron, n-type electrons added. And group 3 for missing electron called gold. In this case, electrons and gold, negative and positive is indicating the group 5 is the negative and the group 3 is the positive gold. That's a dopants used here. And the next case, PN junctions. The PN junctions, a junction between P-type and N-type semiconductor. See here, P-type and N-type in an anode and a cathode is like a simple diode. The PN junction, that is called as the PN junction diode. And NMOS transistor. In the NMOS transistor, 4 terminals you are using. One is gate and a drain, source and a body. That is a source N plus, that plus indicating the added impurity N plus, and source drain, and gate is the polysilicon, that is a metal. In between gate and P substrate, in between one layer is forming. That layer is called SiO2 layer, very thin layer. Even though gate is the no longer made on the material and SiO2 layer, these are the basic NMOS transistor cross-sectional view. Next is the operating the NMOS operation. Here the body is commonly tied in the ground 0 volt in the basic in the initial step. When the gate is at a low voltage, P-type body is at always in the low voltage. Source body and the drain body diodes are here the off state. In this initially no current flows, so the NMOS transistor is off state. In this diagram indicating the initial state, the transistor is off state. And next here, when the gate at the high voltage, the positive charge on gate of mass capacitor and a negative charge attracted to the body and inverts the channel under the type. Now current can flow through the N-type silicon from source through channel to drain transistor. This in this case the transistor is on. So this is the operation. In this case the initial this diagram indicating the no voltage, the initial stage that 0 volt, and in this case that transistor is on state. Here that supply voltage is given, and next that is similar but doping and voltage is reversed. Body tied to the high voltage that VDD, gate low voltage, and in this case gate high was transistor off. Bubble indicates the inverted behavior. So in this case that gate low one state is on state and another gate high for transistor off. So according to the transistor is operating in the transistor act as all are very that transistor act as in a switch condition. Okay, next that power supply voltage at a ground 0 volt. In 80s VDD 5 volt. VDD has increased in the modem process. In IVDD would damage modem tiny transistors, and VDD saves the power. Now VDD is 3.3, 2.5, 1.8, now 1 volt level. In the 80s and all, VDD given for 5 voltage level. Okay, next transistors as switch. We can view MOS transistor as electrically controlled switches. Voltage at gate controls path from source to drain. The first here that the NMOS source, drain, and gate here given, and the PMOS transistor. That's a pull down and pull up. It's a NMOS that bubble indicating in the positive. So one is the off state. First ground this 0 and on state here that mentioning the transistor on state and off state. Both state only is the inverter state. In the CMOS inverter, see here the truth table 0 input and the time VDD, that is when you are giving that input 0, transistor is on state, and input is 1, the transistor is off state. See, this is the operation of CMOS inverters. Is the basic level, and next that off and on, here on and off. So according to the truth table, that CMOS inverter is operating. Similarly, CMOS NAND gate. This is a CMOS NAND gate truth table, and see why I am giving this inverter and CMOS NAND and NAR means that initially that is a very base fundamental basic things. Without knowing that base inverter and NAND NAR universal gates, we can't able to design any type of circuits. So those who are really interested in the research field, first they are implement in the initial step. Initially can design these 3 inverter circuit and NAND NAR. So this helping for all. But myself are given 2 input gates, but researchers and you are taken for 3 input, 4 input, 5. So that's why that VLSI in the 10 to the power gates. What is the meaning 10 to the power means? 1 million gates are internally interconnected. So you can test the entire circuit or design the circuit for uh, one single chip in this. So inverter, NAND, NAR. So nowadays that student or faculty members or researchers without knowing combinational logic circuits and sequential logic circuits, they are directly implementing any type of circuit. They are designing and communication circuits or filters, uh, all those things that and all not possible to get the proper result, proper idea about the VLSI circuits. So everyone that interested researchers can design initially this type of circuit. Then you go for adder, multipliers, encoder, decoder, flip-flop, latches. So these things and all available in ISCA's benchmark circuit. Uh, Google it. You can uh, see the ISCA's benchmark circuits at 85 and 89, where C indicating the combinational logic circuit and S indicating the sequential logic circuit. All type of codes available. What are the input? What are the output? They are available for HDL language and both hardware, that is the VHDL and Verilog codes are available. You can implement, we can design, we can test the all type of combinational logic and sequential logic circuits. The VLSI circuits are only the two category. That is, one is combinational logic circuits and sequential logic circuit. You can implement in the ISCA's benchmark circuits. See, that's why I given basic idea about this inverter, truth table, and circuit operation, and NAND and NAR, universal gate, truth table, circuit diagram, this operation and all. So most of the faculty members know very well in these circuits. So that's why I skipped this point. Here I mentioned the 3 input NAND gate. The 3 input NAND gate, pull down circuit and pull up circuit operation, and these things and all given. See, next we go for CMOS fabrication. See, very, very important thing, that CMOS fabrication. That CMOS transistors are fabricated on silicon vapor. In the silicon vapor, after the lithography process is similar to printing press. Okay. On each step, different materials are deposited or etched, and this is to understand by viewed both top and cross section of wafer in a simplified manufacturing process. This is the initial step of fabrication in the CMOS. And next is a basic inverter cross sectional view, typically used p-type substrate for the NMOS transistor. Is a requires N-well is a sorry for the delay. So the inverter cross section here typically use p-type substrate for NMOS transistor, requires N-well for body of PMOS transistors. In the several there's alternative. This is SOU, twin tap, etc. You are using. See here, in here N plus impurities added impurity here there. The example for N-well, N-well for the PMOS transistor, and VDD supply, and N diffusion, few diffusion, polysilicon, metal. These things and all. There is a cross sectional view for the inverter circuit given. And the next, well and substrate taps. Substrate must be tied to ground and N-well to VDD. Metal to lightly doped semiconductor forms poor connection called Shockley diode. The Shockley diode use heavily doped well and substrate contacts for taps. See in this diagram, substrate tap and well tap is mentioned. In substrate tap is P plus impurities and well tap or N plus impurities. Here the well and substrate taps is given in this diagram, and mask setup here mentioned for transistors and wires are defined by masks. Cross sectional takes along dashed line. See in this dashed lines for the taken along the dashed lines for is a NMOS transistor and a PMOS transistor, well tapped and substrate tapped here mentioned. Here and N plus impurities and P plus impurities are added, and a detailed mask views here mentioned for NVEL, polysilicon, N plus diffusion, P plus diffusion, contact, and metal. See in this diagram, the color codes using the when you are going to design this type of circuits, that time that some color codes are used here. And here I mentioned the fabrication steps. Start with the blank wafer and build inverter from the bottom up. First step will be to form up the NVEL. The cover wafer with protective layer of SiO2 oxide. Here the SiO2 very thin layer here used. And implant or diffuse N dopants into exposed. This is the fabrication steps. And next you go for oxidation. The grow SiO2 on top of Si vapor. Here the temperature range 900 to 1200 degrees Celsius with H2O or O2 in oxidation furnace. In the high temperature only here that oxidation process done. And the next step is the photoresist. In this case, spin on photoresist. Photoresist is a light sensitive organic polymer. Stoppants were exposed to light. In this case, top the mentioned photoresist, and the next layer is the SiO2. Third layer, the bottom layer is a P substrate. The P substrate, this is a silicon layer. So this is the photoresistive method. And next go for the lithography. Expose photoresist through NVEL mask. Strip up expose the photoresist in the top line here, the photoresist. The photoresist and in the next layer for SiO2, and after that P substrate. And finally etching. The H oxide with hydrofluoric acid that slips through skin and its bone, and nasty stuff is very carefully to done in this one. Only attacks oxide where resist has been exposed. In this case, see this diagram in the photoresist part and the SiO2 to and a P substrate. See, and the next one is the strip photoresist. The previous one is the etching, and the next strip photoresist. In this case, the strip of remaining photoresist use mixture of acid called the Piran etch, and a necessary so resist does not melt in the next step. And next NVEL process. That is a NVEL is formed with diffusion or ion implementation. See that diffusion is the place vapor in furnace with arsenic gas. In this case, that arsenic gas the filled, and that you see the furnace, the top line diffuse into exposed Si. See this in this method using the diffusion, and the next one to implementing the ion implementation. Blast vapor with a beam of as ions. That ion blocked by SiO2 that only enter exposed Si, that is silicon only, or exposed silicon is. So in this method, you are forming the N-well process and strip oxide. Strip off the remaining oxide using the HF. The back to bare vapor with N-well. Subsequent steps involve the similar stress of the steps. Here, that N-well is formed P substrate. Here, the silicon substrate. So, and the next one is the polysilicon formations. See, in this process, to deposit very thin layer of gate oxide, there is a less than 20%. There is a 6 to 7 atomic layers. Chemical vapor deposits CVD of silicon layer. Place vapor in furnace with silane gas, SiH4. So forms many small crystals called polysilicon. So heavily deposit to the good. This is the polysilicon formation method. So polysilicon is formed. This is the in the between P substrate and layer is there. That is the silicon oxide. In this method, you forming can use the polysilicon patterning. Use same lithography process to pattern polysilicon. See, in the previous that lithography form in this layer, so that straight that is the straight horizontal form, we can finishing the lithography pattern polyacid and the N-well piece of shade in between. The pattern is forming. Self IC fabrication use oxide and masking to expose where N plus dopants should be diffused or implanted. So what is the meaning of N plus? That is added impurities here, that N plus ions are more and drain and N-well contact. In this diagram, they formed N-well in the previous case and some alignment, P substrate and all mentioned. Okay. And next we go for N diffusion. The previous case for self-aligned process. After finishing the self-aligned process, we go for the N diffusion. Is the pattern oxide and form N plus regions. Self-aligned process where gate blocks diffusion. Because it does not melt during latter process. See, in this diagram, in the process where gate block diffusions are mentioned here, and a P substrate, N-well, this is a cross-sectional of the N diffusion form. And historically, dopants were diffused. Usually, ion implementations today, but regions are still called diffusion. See here, N-well process here implemented for N-well and P substrate and N plus impurities. Gate drain, one N plus for gate, one N plus for drain. According to, we can implement the N diffusion strip oxide to complete step. This is the final step of the IC fabrication. In there, that polysilicon gate SiO2 for the plus gate and drain terminal and N-well in the structure for the strip of oxide to complete the patterning step. See, next we go for the P diffusion. In the previous case, forming the N diffusion. Here that P diffusion, how to forming the P diffusion in the previous, in the N diffusion for N plus impurities. Here that P plus impurities is added, and the same N well method and substrate, but the P plus impurities, that is a positive ion, with the help of that positive P plus to forming the few diffusion and contacts. The final important fabrication method to creating the contact. Now we need to wire to wire together to the devices. Cover chip with a thick field oxide, field oxide. Each oxide where contact cuts are needed. See here the thick field oxide. So I take an example for N-well process. Here N diffusion, polysilicon, gate, drain, source, ground, substrate. These are the main parts of the IC fabrication. And next, metallization. Sputter an aluminum over wall wafer pattern to remove excess metal leaving wires. See, you are going to implement the previous steps, N diffusion, PD, the excess metals are there. So you can remove the in the pattern for excess metals and leaving wires in the same previous what I shown that structure. And layout, chips are specified with set of masks. Minimum dimension of masks to minimize the transistor size. I mean that the IC size are minimizing. And when you are going to minimize the IC size, that time cost also, power consumption also increased, as well as 0 by 0. So accuracy is very, very important. Whatever you are designing any circuit, so accuracy is important. So these factors, speed of operation, cost, important measurements. Future size, that is the distance between source and drain. How to reduce that size? So we can reduce the distance. That when you are using the polysilicon, that time that a gate and a source, that is every 3 future size when describing design rules. Express rules in terms of lambda. So that is called a lambda rule. That is a lambda equal to F divided by 2. Example, 6 micrometer process. Nowadays, using that, all chip designing, IC fabrication is the nanometer size design rules. Say, you are given the that is metal 1, metal 2. In this case, metal 1, that is a spacing 4 lambda. That is a width of 4 lambda here mentioned. Diffusion, polysilicon. Here, the polysilicon normally 2 lambda you are using. 2 lambda for that contacts and 6 lambda each lambda here mentioned. Using this lambda rule, we can simplify it in the any circuit we can designing in the fabricated any. when you are going to reduce that size, we can implement the remaining, that is the power consumption and speed cost, these things and all. And finally, that inverter layout. See, already discussed about the basic inverter. In this basic inverter, in the PMOS 8x2 lambda and 4x2 for NMOS. Here NMOS mentioned for full down and 8x2 PMOS for full up circuit. A 0.6 micrometer process where width equal to 1.2 micrometer, length equal to 0.6 micrometer. So one unit is sometimes called 1 unit for 0.6 micro unit is the 0.6 micrometer process. So according to this rule, nowadays that inverter circuits are designing not only in inverter, all type of combinational logic circuit and sequential logic circuit, or any type of circuits in digital circuits, designing this width and length and lambda, this rule only. So you are discussed about that VLSI in semiconductor, my topic. In this case, that can be viewed as electrically controlled switches. Basically, transistor, that BC147 or here, same thing. MOS transistors as electrically controlled switches and build logic gates out of everything necessary to start designing schematic. So beginners, you can start the inverter, this type of the digital circuit design. You can design very basic fundamental inverter and universal gates. After that, you can implement the whatever your requirement that circuits. And the next important thing, our topic, VLSI digital circuits and AI analysis. How that VLSI helps in the automation, AI in VLSI design automation. I given some AI flow such as placement and routing optimization. Machine learning model. Nowadays, the very familiar model for machine learning models predict optimal component placement and interconnections. Design space. AI explores architectural configuration to meet design constraints. Power, performance area. All are focusing in power and performance, speed, and reducing the memory size. That is the entire size. That's called area. So this and all AI perfectly doing in the DSE. Next, EDA tool enhancement. AI is integrated into electronic design automation. That is called EDA tool specification. So nowadays, for design automation. So these three design automation in the VLSI, in the AI, the first thing is here analyzed. Next, second one, and the fault prediction, concentrating in the fault prediction. Suppose many company, top MNC company or small startup company, they are manufacturing in the any type of circuits, that's VLSI circuits. That VLSI circuits giving the good result or not. That is a very important task. So we can finding the fault prediction and testing. That is called the testing is very important. With the help of AI is the crucial in detecting, predicting, and isolating fault in VLSI circuit. In earlier days, we are using test selective trigger scan architecture, some different more time. It will accuracy result. But nowadays, that AI is giving the prediction in under vector mechanism are used to classify and predict manufacturing defects. So AI playing the big role in AI fault prediction. Next, built-in self-test patterns and reduces test time and power consumption. So in earlier, same built-in self-test, it will operating more fast and giving the accurate result. And the third important for yield vapor test data to predict yields. Say is playing the big role complex process variations. So nowadays using for the AI models compared to very less accuracy. And